not going to do the sandwich theorem, and we'll get your test and go over some key points that were missed. Now, one thing I want to do before I do this is talk about distributive properties. You can distribute 2 times 3 plus 4. That's allowed if you distribute multiplication over addition. Don't get that mixed up with 2 times 3 times 4. Totally different. But the problem is a lot of you like to do this. You want to square root 3 squared plus 4 squared and say it's 3 plus 4. That's really doing it 3 squared plus 4 squared to the 1/2 power. And what you're doing when you say it's 3 plus 4 is you're distributing that exponent over addition. Well, guess what? It doesn't work. You can't distribute an exponent over addition because this is the square root of 9 plus 16, which is the square root of 25, which is equal to 5. Whereas if you distribute here incorrectly, you're going to get 3 plus 4, which is 7, and they're not equal. For a love about math. If you do it a different way, you got to come up with the same right answer. So that's one of the problems that I will see throughout the year. Distributing everything. Can't do it. But what's nice about limits is you can distribute limits. That's allowed. And these are the properties of limits. And I'm just going to rewrite it a little bit because it kind of looks like a lot of Greek there. And all this is saying is that you have the limit. If I have the limit of f plus t, that's equal to the limit of f plus the limit of t. Is it fixed? Yes, let's do this here. Okay? So you can distribute the limit over a sum. You can distribute a limit over a subtraction problem. If you have a constant, so if I have the limit of sorry, if I have the limit of a product, then I can do the limit of f times the limit of t. Now there's a condition here. I can only do that provided that each individual limit exists. In this class, we're always going to have them exist. It's not going to be a problem. If you see the class, I will be giving them some activities where the limit of the product will exist, but the individual ones do not. You cannot use this theorem to the problem. The only way you really should be finding limits is looking to the left and looking to the right. I also can do a constant. If I have a limit of some constant times f, I can pull that constant out front. And you're going to throughout the year and say, well, why'd you do that? And I say, because I made a limit. Because I used this the limit of f. Plus, I can also do the limit of division of the function f over t can be written as the limit of f divided by the limit of t. You're not going to write down all those steps. You read the book and show an example of that. You won't be doing that, but you'll be doing it automatically without writing all that stuff. And then I didn't like the way they did the power rule in number 6. And, R over s is basically a fraction. That's all. I just look this way. If I have the limit of some function to the nth power, what I can do is find the limit of the function first, find that answer, and then raise that to the nth power. Well, egg could be a fraction. That's all. So those are the properties. So if you want to do that, well, you can't do that like with exponents, but you can still do that. That's called the main limit. You're never going to have to state this ever. You're just going to be able to apply it. Okay, this is kind of difficult to read as well. This is right out of your book. This is a polynomial. And polynomials, all they're saying is that the powers n has to be equal to whole numbers. No negative, no fractions, whole numbers. So they're saying if we have a polynomial and I want to take the limit of my polynomial, I don't have to check for both sides. There's no problem with the polynomial. This is exactly equal to the value of the function at c. So all I have to do is substitute in my c value of my polynomial, and I'm done. I don't have to look at the left. I don't have to look to the right. But the problem is if you don't recognize your polynomial, then you better check. You really always should check. But this is a theorem that lets me not check. If it's not a polynomial, then you are going to have to check from the left and then check from the right. That happened last year. You got to fight that problem. And if f and g are polynomials and c is any real number, again, if I have a ratio of polynomials, so it's the limit of f of x, really it's this, as x equals to c, over the limit as x equals to c of g of x. You may just go ahead and substitute in there f equals f of c over g of c, provided that g and f are polynomials. Sine and cosine work that way too. Tangent, we got a problem. We have to break the red. Absolute value does not apply. Absolute value has a vertex. But if they're nice, smooth functions, they do things like this, no breaks in the red, then you can just evaluate the function like that. And most times you're going to give you something that's 0 over 0 in it anyway. Okay, that's the main one. Now what about these trig functions? Okay, what about the trig functions? Which are the ones we have to know? We have to know that the limit as x goes to 0 of the sine of x over x is 1. That's one we have to know, memorize it. Can't prove it like increment easily for geometry. And then the other one is this is the limit as x goes to 0 of the cosine of x minus 1 over x is equal to 0. You can also write it 1 minus the cosine of x over x. And let's do one other thing. Let's write this down with it. I can also write this one. What if I do the reciprocal of this function? What's the reciprocal of 1? So its reciprocal, we can see that, is also equal to 1. Can I reciprocal to 1 with this cosine to the 0? No. Because if I reciprocal 0 over 1, the reciprocal would be equal to 1 divided by 0, which is 1. Okay? You got to keep this in mind as we do these problems. Now, the only place we have issues is when I get 0 divided by 0. If I get a number, it's not a problem. It's easy. So let's go ahead and substitute in 0 here. What do we get? What's the change in 0? It's 0. And that's 0. If you forget what the tangent function looks like, I know what this will look like. It looks like this. So that I know that the tangent of 0 is 0. Okay, so let's do this problem. Now, once I do this problem, you may use this problem. There'll be a theorem that's proven, but I have to prove it. Now, you have to convince me that you know what you're doing. Remember that. What's tangent? Sine of x over cosine of x. And that's all over x. You still have 0 over 0. But I don't care. If I evaluate something and it's not 0, I can do that at any point in my process. So if I put 0 for sine, I got 0. Put it for this plain x, I get 0. But if I put it in for cosine, I have 1. So what I do is when I do these trig ones, or any of them, I evaluate the things that are not 0. Cosine is not 0 at 0. Pi over 2 it is. I can do that. That's allowed. So this becomes, and it becomes a lot easier. So that's a complex fraction. And you have to figure out where the x goes, etc. Just get rid of the cosine because this now looks like this. And this is the sine of x over x. And so it changes it. Now it bothers you that I evaluated the cosine of x. At least it has in the past, but it shouldn't. The only places I have issues are where I get zeros. That's it. Remember the 4 things. You can get a number, you can get a 0 divided by a number, you get a number divided by 0, or you get 0 over 0. 0 over 0 is the only place I have a problem. I just evaluated it. Because this is the cosine of 0, which is equal to 1. I'll be doing it a couple more times. 0 over 1 over 0. What's 0 divided by 1? I can do that. That's 0. So it's still 0 over 0. Didn't solve my problem, the 0, but it cleaned this up, and I got rid of it. Because I can't. I don't. If the cosine function were 4, I could do the 4. I would still have to extend with some of the algebra in the complex fractions. But the fact that it's 1 makes it really nice. The sine of x divided by 1 is just sine of x. I'm only evaluating the one that's not 0. Because the only issue is 0. You can do a number divided by a number. You can do 0 divided by a number. That's no big deal. You do a number divided by 0. We'll deal with that next week. And then if it's 0 over 0, I can evaluate anything that's not 0. Okay, so let's try a couple problems. Now, one of the things is these are all properties of algebra. I could divide them. This really is 1 over x times x plus the sine of x. That's what this is. So if I divide x into both terms, then I can maybe make the problem a little easier. Now, these are probably right out of your textbook. It may be a homework problem. But let's go ahead and divide. X goes into x number 2. Well, actually, write it down. So I get x divided by x plus the sine of x divided by x. Simplify. Except you have to simplify. And that's 1 plus sine of x over x. Now, you're going to go right to the answer, but I'm not. I'm going to show you the main limit term and how it applies. I distribute the limit over the sum. So this is the limit as x goes to 0 or 1. You do not have to show this. You can go right to the answer if you see the answer. If you don't, you might have to show it. What's the limit of 1? This is the y value. The horizontal line is 1. The limit of a constant is the constant. What's the limit of this one? 1. So the answer is because x is a question. X over x can be reduced because guess what? We're never at 0. We're near 0. As long as we're not at 0, I can reduce this x over x. Remember, we don't care what happens at 0. We're near. So if I have 0.001 divided by 0.001, isn't that just 1? You do, and I forgot to do that. That's 0 over 0. Right? 0 over 0, which tells me I can't stop, right? It works. Okay, this is a tricky one. Example 3. You'll find this hard. In fact, before I do that, let me do this. Okay, we have this, the limit, as x goes to 0 of the sine of x over x. What if I have the limit as 2x goes to 0 of the sine of 2x over 2x? You should get what? 1. But it doesn't matter what this is. These have to match. I could call this y, sine of y over y, and if x goes to 0, 2x goes to 0. Then y goes to 0. They're dummy variables in here. I could put h's in here. I could put y's in there. I could put anything I want. So as long as these match, I can use this theorem. So I'm going to do that. Can I pull, is the sine of 4x? Pardon? That still equals 1. Doesn't matter what that number is. So if I have the limit of star times x goes to 0, sine of star x over star x, that's still equal to 1. I could do a substitution. I don't want to do that because it'll take longer and you might as well just learn the easy way. Now, first thing, can I pull this 3 out? Yes. The 3 kind of gets in the way, so let's just pull it out. Ready? Now, here's my little whiteboard magic. Not really, but let's do a fraction. I'm going to write this as the sine of 4x over 1 times 1 over the sine of 3x. It's a trick. Do you believe that's still the same thing? Because if I do 1 times sine of 3x, I get sine of 3x. If I do 1 times sine of 4x, I get sine of 4x. And now knowing that I want to get what I have up here, some number times x divided by some number times x, I could get this to work if I had what in the denominator right here. What would make this work? Just a 4x, right? These would match. If x goes to 0, would 4x also go to 0? Yes. We can make that a 4. Now, I've unbalanced this, haven't I? So where else I have to put a 4x? In the numerator. Because I can only multiply by 1. I can't pull the x's through because this is operating on x. But everything else, constants, or if there were y's in there, I could do that. Okay, so we're going to get 3 times, as we have the limit as x goes to 0. What's this one going to get? I'm not going to show all the steps because that's, you'll just do it this way anyway. This is 1. Pardon? Well, I'm not getting rid of it. It's right there for us. It's not distributive property. Multiplication. Distributive property, multiplication over addition. There's no addition. Okay, what's this limit? That's 1. And I'm left with 4x over the sine of 3x. I'm not sure what you want to do. No, it's not distributive. Distributive has a plus. Don't have a plus. No, you can leave the constant out. What's the other constant I can pull out now? Let's pull the 4 out. Okay, so I'm going to do one step at a time. So this is 12 times the limit as x goes to 0, and I am left with x over the sine of 3x. What do I have to have up here to make this? I have to have a 3. And I have to have what? A 3 in the denominator, right? Is that fair? Because what number is 3 divided by 3? 1. I'm taking the value. Now, can I pull this 3 out? I want that one there. Can I pull this one out? There, I can do that. Divide by. And what's this limit going to give you? Since it all matches, these match. 1. So 12 divided by 3 is 4. In a sense, it's a little bit harder. Is the sine of 4x equal to 4 times the sine of x? Is that true? It's equal to 4. Guess what's 12 divided by 3? What's this? What's this limit? It's 1. It's one you have to memorize. Upside down, that's okay. Remember when I went through that? Let's go back. I said it could be upside down, you still get 1. Okay. What? What's 0? This is 0 over 0. It's that special limit of the sine of x over x. Okay, you guys. Question. Is the sine of 4x equal to 4 times the sine of x? No. So don't do that. I will require all this work. Some of you are going to look at it and say, well, it's just 3 times 4 divided by 3. You're right. You can use it. Check yourself, but you're going to have to show the work. Oh, we're not done. We'll do some more. We'll do also the ones on your worksheet. So I can't pull the x out because the limit has to do with x. So it's the limit as x goes to 0. Well, should we go ahead and write tangent? Well, by the way, is it 0 over 0? Yeah, it is. Because the tangent is 0 and x is 0. This is what? Sine of 3x over cosine of 3x. And in the denominator, we have x times, what's this? Oh, 1 over cosine. Now, I don't care about things that are not 0. Things that are 0 give me a headache. But the things that aren't 0, I can evaluate right now and get rid of them. What's true about the cosine of 0? No, it's not. It's 1. Okay? So this is equal to 1. And this is equal to 1. I just want to make this a little simpler. So now, when I simplify that, it's the limit as x goes to 0 of the sine of 3x over x. I mean, I could pull it out and do something with it elsewhere, but this is just 1. Remember, I can evaluate anything in a limit as long as it's not 0. It costs me no trouble. So let's just go ahead and simplify this right away. And now, what do you have to have here to make this one work? I got to have a what here? 3. Because what's the cosine of 3 times 0? I said you can put 0 in if it doesn't cause me trouble. What's the cosine of 0? 1. As long as it's not 0, I'm fine. As long as the output is not 0. Now, I put a 3 there. Okay, you guys? What can I do with this? Oh, I go. That's not right. What else do I have to do? Okay. Now, what can I do with the 3? Take it out. Oops, keep it in the numerator. So it's 3 times the limit of the sine of 3x over the sine of 3x over 3x as x goes to 0. Certainly 3x goes to 0 as well. We can't be proper about it. And this is going to give me what? I multiplied by 3 over 3. It looks far away. And then, what about that? Yes. Well, not cosine of anything, cosine of 0. So 2 times 0 is 0. Right. So the cosine of any number times x, x being 0, is always going to be 1. So that makes everything so much simpler if you do that. I can evaluate them and they're 1. Not cancel. What? You guys can't hear it. Then they can't do that. Well, I mean, I can do it. That's not the problem. See, here's what you're going to get. Trust me on this. If you do not simplify the cosine, you're going to get this. The sine of 3x over x, and then this cosine is going to go in the denominator, and that one's going to go in the numerator. Cosine of 2x and cosine of 3x. And this limit is still, once I put the 3's in there, will give me the 1, and these are 1. So see, it doesn't matter. I don't want to deal with the complex fractions and get these in the right places, because I'm probably not going to do it right. Well, I don't know what you can do. So anyway, just evaluate it, because it's 1. Now, if we're 5, then it does matter where I put them. But it's 1. So it's not going to make any difference. Keep it simple. Because these have to match. So if this were a 5, I'd have a 5. And I could do it with a substitution and prove it to you. Pardon? Because I have to multiply by 3 over 3. I can't just multiply. I can't do that. That's not legal. I have to make it work. I have to multiply by 1. So these have to match. And I just pulled it out. Okay? The next thing's the syrup, but we're not going to do that. So let me go ahead and save this. I pulled one of them. I could pull both out, but then it doesn't do me any good. I mean, I could pull this one out too. What? I could pull that out, but now we can't do this side because it doesn't match. This is 1. The sine of any number times x over the any number times x as x goes to 0 is 1. Doesn't matter. I could do a substitution if you want me to. Okay. Are we done? You have to use parentheses. Okay. Now, let's do these. And, immediately I look at this and I do it wrong because I don't read it properly. This is your worksheet. Only the front side. I haven't done the back. We'll do the back later. The days of memorizing have ended. You have to think, and you'll find that thinking is easier. If you continue to memorize, you will hit the wall. Eventually, you won't get it. You can't. Yes. Everybody had their worksheet out? And I said you couldn't do these three problems. No. Let's do them. Now, first thing I could do is I could take 3 out of there, but I don't really have to. But let's do it. Then read the problem carefully. If you substitute, you'll realize this is not 1 because x is getting bigger and bigger and bigger. This is not, x is not going to 0. So look, we're going to have to think a little bit. So the sine of x is a finite number trapped between what 2 numbers? Negative 1 and 1. It's just a simple number. Let's just say it's 1. Could be a fraction. And x is going to get to be really large. So if you took $1 and you divided it among a million people, in effect, how much would everybody get? No, if I have $8 and I want to give it to everybody, divide up with everybody in this class, yeah, you get $1 million of $1, which is essentially what's the limiting value. 0, you get nothing. It's like the lottery. Your chances of winning are 1 out of 55 million. Okay, it is slightly bigger than not playing the lottery at all, but it's so minimal. I don't play the lottery. It's not worth it. It's throwing money away. This is 0. Your chances of winning the lottery are 0. If you don't buy a ticket, it's absolutely 0. So if you do buy a ticket, you have a teeny tiny chance, but in effect, okay, let's do this one. Let's put 0 in. Do we get 0 over 0? Yes. Okay. So we're going to do a little work. And I don't like the tangent. So I'm going to change it because I know what tangent is. It's what? Sine of x over cosine of x. Okay, Grant? Question? Yes, 0. This is one where you think, as x gets big, this number is a finite number, and that number is getting bigger and bigger and bigger. Put it in the graphic calculator, you'll see that it's going to be very close to the x-axis. Okay? If I have $1 and I divide it among a billion, everybody on this earth, everybody's going to get nothing. So that can only go to pennies. Okay, what about this one? What can I do next? What can I do to make this easier? Let's get rid of the cosine because it's not 0. 0 is the only place I have problems. So when I do that, I'm going to get the limit, because what's the cosine of 0? And I'm going to get the cosine of x minus 1 over the sine of x. Do I still get 0 over 0? Yes, that's what the problem is. Okay, so I'm going to do the same trick. I'm going to write this as 2 fractions. The limit as x goes to 0 is the cosine of x minus 1, and this is the sine of x here. That's just multiplication of fractions. That's all that is. And I'd like to use one of my special, or maybe both of my special limits. One has to go here, and then or here. Both make this equal to 1. If I put an x in there, then I need to put an x in the denominator. Now, if you want me to write this as a product of 2, I will. Or you'll just do the problem, probably. I don't like to write all this stuff out. Times the limit as x goes to 0 of x over the sine of x. Now, those limits do exist. You have to write limit every time. You need to write this last line? No, you can just tell me what the answer is. Because what's this going to give you? Look it up on your notes. What's this going to give you? 0. What's this going to give you? 1. So what's the answer? 0. Did you have to write this line right here? No. I just did it to show you the main limit there. Okay, we got more to do. one more trig one. How about this one? The limit as x goes to 0, some of you are going to say, well, the answer should be 5x. You were right. You were going to get no credit. Because you have to convince the reader that you understand why it is 5x. And I know that there are some people who think I can pull the 5 out and I'm distributing. I can't do it. Which one do you want to work with first? The first fraction or the second fraction? Remember, I want to get the sign of something over something. These have to match. That's what I want to get. Want to do the 5x? So if I put the 5x here, and then I put the 5x here, okay, then what? I mean, I could write this as a product of two lines. You can do it anytime. As long as it's equals what? What's this one? 1. What can I do with that 5? Oh, I thought we separated. Okay. So it's 5 times the limit of x over the sine of 2x. Now, what do I have to do to make this one? Put a 2 in here, and then put a 2 here, right? Everybody with me? These have to be equal. 2x and 2x. Okay. Guys, quiet. This 5 is a constant. I can't pull the x out, but I can certainly pull the 5 out. And guess what I'm going to do? I'm going to do the same thing here. Because I have 2x over 2 times sine of 2x, I can pull this 2 out. I can, but if I take this top 2 out, it's pointless. Because I need to have a 2x here and a sine of 2x there. I evaluated that one. So it doesn't help to take this 2 out here. It helps to take the 2 out there. So what's the answer? This is equal to 5 halves times, what's that one? Okay? Getting okay with that? You got to practice with these. I can find more. There aren't very many in your book. Okay, now we're to something a little easier. What should you do? Oh, question. Abby. Okay, shh. Because when I have the sine of 5x over x, that limit doesn't work. So I have to put a 5 here, and I have to put a 5 here. And this limit is 1. And then I had the limit of x over the sine of 2x as x goes to 0. Again, that one doesn't work. I need what here? The 2, and to keep things fair, I have to do a 2 here, right? I don't pull the 2 out of this one. I'm pulling out of the bottom one. No, it's in the denominator. Okay, we want to get our test back. So, we have to finish this worksheet. Yeah. Okay, guys, ready? What you do first? You know what I did? I factored it because I'm silly. Yeah, you should be able to do this one. What do you get? Negative 16 over, which reduces. By the way, that's a fine answer on free response. No reason to even simplify the negatives. It's 2/3. You don't get 0 over 0. So don't forget to always substitute first. Okay. Now the next one, 5 is tricky. It doesn't exist on 5. Did you check for both sides? Because you came in for some help. Okay, guys? It still works. You're just wasting your time. Okay, this one. we have to figure out what this absolute value of x plus 1 is equal to in a piecewise function. So absolute value is just this. What's the 1 going to do to my graph? Move it to the left. The only place I have issues is at that vertex. So what is the equation for this curve? It's just x plus 1, right? If x is greater than or equal to negative 1. And the left side of the graph is opposite of that. Just like what we did on that other worksheet. Now I'm going to have to write my problem 5 as a piecewise function because I have to check from the left and I have to check from the right. I don't have to write it as piecewise, so let's go ahead and do it. By the way, you know you get 0 over 0. And so you're going to factor that. So it's going to be the limit as x goes to negative 1. Let's do the right-hand side first. It's this one, and factors 2x minus 5x plus 1, correct? Now, what's the denominator since we're coming in from the right side? What's the denominator if we're coming in from the right side? X plus 1. I got rid of it. I'm looking from the left or the right. Oh, type in ABS. Okay, what happens to this? And what do I get when I put in negative 1 in here? I get what? Negative 6. I know this is a pain, but guess what? You've got to do it from the other side. This is not a polynomial. The numerator is a polynomial, but the denominator is an absolute value. And it doesn't, there is no theorem about that one. You can make one up as well. Now, what if I come in from the other side? What will I replace the absolute value with when I come in from the left side? Not x plus 1, but what? This guy. Okay, what happens to x plus 1? Put the negative 1 in, and I get negative 6 over negative 1, which is positive 6. Well, on the right side, it's negative 6. On the left side, it's positive 6. It does not exist. Forever recorded. Does not exist. The left does not equal the right. No. Undefined will be infinity. It just doesn't exist. Can you just plug in negative 1 in the original equation? Yes. You get 0 over 0. But the problem is, because this denominator is not a polynomial, right? Because this is not a polynomial, you can't just substitute it. You have to look at it from both sides. You always need to look at it from both sides, but there's a theorem that says the right and left side will always be equal in a polynomial. All right, I like to make things easy for myself. Okay, what did you do with this one? By the way, what's the answer to this one? Yes. What did you multiply by? Are there questions on this? Okay. So it's in the algebra. Okay, ready? Now I chose to rationalize the numerator, so that's the one I want to multiply. That's x minus 4. Some of you distribute it here, and then you have to factor it back. So just leave it as multiplication problem. What happens to x minus 4 is now? And so you end up with 1 over the square root of 4 plus 2. Or 1 4. How about number 7? What's the answer to that one? It's 1 because you get negative 6 over negative 6. Substitute. I'll bet there are questions on 8. Yes? Questions on 8? 1/30. Now, I'm gonna rewrite this because I really don't feel like I have enough space there. This is one I made up. This is the limit as x approaches 5. First put 5 in. Well, I have to recopy the problem. And tell me if that's 0 over 0. Now, this is a complex fraction. And I think a number of you were taught you get common denominators, and then that's division. So then you would multiply by the reciprocal. That's too much. Let's not do that. Let's clear out the fractions. So what I'm going to do is multiply the numerator and denominator by the least common denominator for these guys. Well, it doesn't have to be least, it's just approximate. So if I multiply them together, it's x times x plus 1. Now the fatal mistake is right here. If I just do that, I'm going to be in trouble. I must also multiply the denominator by x times x plus 1. But some of you forget to do it. Either you forget to do it or you say, I'll do it later, and then you forget to do it. Doesn't matter, problem. So always make sure your mathematical statements are correct. Now you will not have a problem. It tells you what to do. So I'm going to distribute that. It says distribute. That times this one, and then that times this one. This one we're going to leave as a multiplication problem. So I'm going to get the limit as x approaches 5. Should be ahead of me. And what happens to the x plus 1s when I multiply this at the first term? They cancel out, and I'm left with a 6x. Now, I have minus 5, and I must have parentheses. Some of you like to distribute right away, but you're going to make a mistake because you're not going to distribute a negative sign. No, we've got to have that negative sign. So what's going to cancel out here? The x's. So it's 5x plus 1. Remember, I've been using this a long time. That's what the mistake is. Forgetting the negative sign. And that's over. Just leave this multiplied. Don't multiply it out. X minus 5 times x times x plus 1. Can I cancel the x plus 1? It's up to you if it is. No. If I had parentheses on 6x minus 5, I'd be allowed to do that, but I can't. So now what I have to do is simplify that numerator. So nothing I can do with 6x, but I can distribute the negative 5. What do I get? Minus 5x minus 5. If I make it plus 5, nothing will cancel out. Let's say I make that mistake, but I had 0 over 0. That means I made an algebra mistake. Has to cancel out. So it's x minus 5, x plus 2. You add the numerator there, so you add similar terms. Yeah, what's 6x minus 5x? Yeah, so it's the limit as x approaches 5. Then x minus 5 over, and that's times 1, so this is a multiplication problem. X minus 5 times x plus 1. There's the whole, the x minus 5s. So if you had gotten x plus 5 by accident, then you say I made a sign error because something has to cancel. I had 0 over 0, something had to cancel. Don't know what it is. Then go back and look at it again. So what happens to x minus 5? They go away. Substitute in 5 and you get, notice I put the 1 there, I'm not going to make a mistake. 1 over 5 times 6, 1/30. Plus. Okay? Are we okay with that now? Yes. Let me stop this.